Now, it is easy to show that, okay, it can be observed that the closed loop transfer function of a positive feedback system. So, feedback system with everything else remaining the same, right? So, only thing is we have positive feedback. What do I mean by positive feedback? Here, instead of subtracting, I add. Okay. So, let us say if I have a positive feedback system, by and large we are going to consider negative feedback, because ultimately we want to subtract signals and get the reference, get the difference from a practical perspective. In some cases you may have some algebraic manipulation where you may need to add the signals at the summing junction, okay, it may happen, okay. But in this course, by and large, we are only going to consider negative feedback, okay. I am just pointing this to you. If you encounter a system with positive feedback, that means that only difference being that at the summing junction, you have two plus instead of a plus and a minus. So, immediately you will see that this you can derive as homework. What is going to be the only difference? The denominator will become 1 minus g of s h of s, okay, because what is going to happen? This minus is going to become plus, okay, this minus will become plus. So, everywhere this right hand side will become plus. When you take it to the left hand side, it will become 1 minus g of s h of s, okay, that is the only difference you are going to get if you have positive feedback, okay. That is the closed loop transfer function of a system with positive feedback, okay, with all other elements remaining the same, right. Now, some more terminology, okay. So, suppose if I break open the loop at this point, okay, suppose let us say I have a closed loop and I break open the loop at this point, whatever transfer function I get, okay, which relates the signal at this point, okay, which is W of s, to what goes as the input to the system, which is E of s, is what is called as the open loop transfer function, okay. So, let me derive it, okay, then we will come back and look at the definition once again, okay. So, what is W of s? Let me derive W of s, okay. So, what is W of s? W of s is going to be H of s times Y of s. Y of s is going to be equal to what to say P of s times U of s, and U of s is going to be equal to C of s times E of s, right. So, this is nothing but G of s. So, we are going to get G of s times H of s times E of s, okay. So, this implies that W of s divided by E of s is what is called as G of s times H of s, okay. So, this is what is called as the open loop transfer function, okay. That is the term which is given to us. Why is it called open loop transfer function? As I told, look at the ratio of the signals that I am taking, right, W and E, right. So, as I told you, imagine that you cut open the loop here, right, you open the loop, okay. The signal that you are getting at this junction is going to be W, and the input to the opened loop is going to be E, right. So, that is why we are essentially taking W of s divided by E of s as the open loop transfer function. That is a definition, okay, and that is going to be G of s times H of s, and the once again, let me just go to the next page and come, okay. The poles of the open loop transfer function, let me abbreviate as OLTF, okay. I am abbreviating this as OLTF, are called as open loop poles, okay, right, and the poles sorry, the zeros. Oops. The zeros of the open loop transfer function are called as open loop zeros. Okay, so that's once again some terminology we should remember. Okay, so if you encounter the adjective open loop, we are talking about G of s times H of s. Okay, so I hope it's clear why it's open loop, right? So I'm opening the loop, right? So you may ask me the question, hey, is it going to be something which is physically meaningful? Not necessarily, okay, but you will see that, like this is going to be used, right? So that is, it is an indicator of what will happen without feedback. Okay, that's what we are doing. Suppose, like, let's say I put all these elements in the loop, but I don't close the loop, right? Which I will never do in practice, by the way, right? So see, then what is the point of designing a closed loop feedback system, right? Suppose if I don't close the loop, what is the transfer function I'm going to get? Okay, so that is what is called as open loop transfer function. Why is it important? What is the open loop transfer function? G of s times H of s, right? G of s is C of s times P of s times H of s. So you see that the open loop transfer function is nothing but the product of all the transfer functions that you have, right? So you have three blocks, right? C of s, P of s and H of s. You see that immediately the open loop transfer function is formed by the product of these three transfer functions, right? That's why you will see that it's useful, okay, as we go along, okay? Yeah. Any questions? Yeah. Once you open it, yes, they become the same, right? So yeah. So for that reason, some people will define open loop transfer function as W by R. Okay, we should not just lose track of the fact that once you open the loop, R and E will become mathematically the same. But once again, it's a hypothetical opening, right? So that's what I want to just alert you. And you can immediately see. We will when we go to what to say, advanced tools, that we used in control design, you will see the impact of this open loop transfer function. Immediately you see that the closed loop characteristic equation is 1 plus open loop transfer function. One can immediately observe that, right? So if you look at the closed loop transfer function, what is the closed loop the closed loop characteristic equation? 1 plus G of s H of s equals 0, right? So the closed loop characteristic polynomial, which is the denominator polynomial of the closed loop transfer function, is nothing but 1 plus open loop transfer function, right, for negative feedback systems, right? So you will see that, we are going to use this to our advantage, right? So we will see that, okay? So please remember this, okay? And one more thing which I want to point out here is that in many textbooks, many references, the same block diagram is redrawn in this manner. Let me redraw it, then we would discuss it, okay? So is this color visible? Is it fine? Sorry? Okay, yeah. So, so what happens is that in many references, we will see that the same feedback diagram is modified in this way. I hope it's clear why it's done, right? So because G of s is nothing but the product of C of s and P of s. So what people do is that, let me draw this with this golden color. So what we do is that, like, we just combine these two blocks, right? Once I combine it, right, the input to this block is E of s, the output to the block is Y of s, right? Y of s is going to be G of s times E of s, right? So we already have got that, right? So that's it, okay? So if you look at Y of s here, so why did I do it this way? Like you see that Y of s is going to be equal to P of s times U of s, which is nothing but P of s times C of s times E of s. So you immediately observe that Y of s is going to be equal to G of s times E of s, right? So people will just combine the controller and the plant block and then write it in this form, okay? So these are just various visualizations of the same feedback system. Is it clear? Okay, fine. Any questions? Yeah. Okay, So now, as I told you, where are we? Okay, we are still looking at P of S, right? So we are still in the plant transfer function. So we are once again analyzing the plant or the system. But as we move along, we will extend the concepts to the entire system. Okay, so now we are looking at whether a plant is stable or not by looking at the poles of the plant. So when we design a closed loop feedback system, we want the closed loop to be stable. So we look at the closed loop poles. Okay, we'll extend it to the closed loop transfer function. Okay, so that's something which we are going to do. And one important thing is that in any control design, okay, a control designer should look at two important aspects, okay, in this order. The first one is that of stability, okay. The second aspect is that of performance. Okay, there are two aspects, stability and performance. Okay, so both are important, but stability is more important than performance, right? See, if I do not have a stable system to begin with, like I can't even talk about its performance, right? First, I should ensure that the system I am designing is stable. Then we talk about performance. Okay, so what I'm going to do is that I'm going to draw a dashed arrow to indicate that like when you design, both are important for a control designer, but first you ensure stability, then we talk about performance. Okay, so now what we are going to start discussing from now is that how can I quantify performance, right? So that's something which we are going to learn, right? So we are going to learn about performance specification, right? So what we have done is that we have looked at stability, the notion of stability that we are going to follow in this particular course is that of bounded input, bounded output stability, and we have seen that the criteria for ensuring Bibot stability is that all system transfer function poles should be in the left of complex plane. Okay, so that's the criteria, right, for Bibot stability, right? So now the question is that let us say, I ask, there are, let's say, 60 of us in this room, right? And let's say, we want to develop a controller. Let's say, a controller for regulating the temperature of air in this room, right? Now, let's say all 60 of us design stable systems, stable controllers, okay? Now, I have 60 controllers in my hand. How do I evaluate which is the best one? Okay, right? So from a practical perspective, I need to evaluate, right? So then what can be some, parameters which I can use for evaluation? What do you think I can use as criteria for performance evaluation? How fast it will? Very good. Okay, so let's say I come into this room in summer. Okay, let's say the room temperature is, let's say, 38 degrees Celsius, right? I want it to go to 25, right? I look at each controller, right, and then I set my reference as 25 degrees Celsius. I may evaluate how fast it will go to 25. That's one. Very good. Okay, then accurately it can maintain it around 25. How fast it can settle around 25 and how close will it remain to 25, right? See, if I have an air conditioner, let's say, which goes from 38 to 25 in 10 minutes, but then it remains, between 23 and 27, I will not be very happy, right? So let's say it cuts off at 23 degrees Celsius and cuts in at 27 degrees Celsius, right? So I will not feel very happy, right? Because I'm going to have a 4 degrees Celsius variation, right? But on the other hand, let's say a air conditioner maintains the temperature between 24.5 and 25.5. I may be very happy, right? So that's one performance specification, right? So then how fast it will settle, right? How fast it may overshoot the value. That's what we have also looked at, right? So there is, I have given a reference value. How fast, how far away will it go from the desired value, right? That's another performance specifications, right? What are the steady state errors, right? So the speed with which it will go to the final desired value, the band to which it will regulate around the final value, right? How much it will overshoot the final value or the desired value, all those are performance specifications that we would be interested in, right? And that's what we are going to learn and quantify, right? So typically the prerequisite is that the system is stable. Okay, that's why I discuss stability first, right? So because without stability there is no point in discussing performance, right? So as a prerequisite, like I want my system, I can only do performance analysis of those systems that are stable to begin with. Okay, and typically parameters that are used to specify performance or quantify performance, I should say, are extracted from the step response of first order and second order systems. Okay, so we see why, right? So typically the parameters that quantify performance specifications, performance requirements are motivated, right, and calculated. The formulae are extracted from the step response or the unit step response of what are called first order and second order systems. Okay, we'll see why, okay, as we go along. Okay, the motivation will become clear when we go to advanced control design. You will see that we learnt about dominant poles, right, yesterday. So by and large, even if you have a 10th order system, okay, by and large, okay, you are going to have a dominant dynamics that corresponds to a first order system or a second order system, okay, by and large. Okay, there can always be exceptions. Okay, typically you are going to have the dominant dynamics which can be captured by a first order or a second order system. Okay, that is why we are motivated in using these systems for extracting performance parameters. Okay, we would revisit this point later, right? Okay, so consequently let's start today with first order systems. Okay, so I am going to start with a typical first order system model, and I'm going to leave you with a set of questions. Okay, so what is a first order system? The governing equation of a typical first order system. See, in fact, like it really depends on whom you talk to. Suppose, let's say you are discussing this, this with a chemical engineer, for example, right? They would say a model for a first order process. Okay, they will always be looking at processes, right? So they will be modeling chemical processes, right? The plant for them is a process. Okay, so if you look at references that are written by chemical engineers, they will say that, oh, it's a first order process. So please don't get confused. It's the same thing. Okay, so for us we are looking at systems, right? So we are using the term system. Okay, they may use the term process. Okay, that's the only difference. Okay, so first order system, the governing equation of a typical first order system is capital T times dyT dt plus y of t is equal to u of t. Okay, where t is a real number. Okay, fine. So what is the transfer function of the system? Take the Laplace transform on both sides what do we get? We get t times s y of s minus y0 plus capital Y of s is going to be equal to u of s. Correct? That's what we are going to have. Right? So, of course, to calculate the transfer function, what do? We assume 0 initial condition. This implies that y of s divided by u of s is going to be equal to 1 divided by ts plus 1, right? So, this is the Planck transfer function. Correct? I hope everyone agrees, right? Pretty straightforward. Now, from this, what are the values of n, m? See, I just want to you to develop these things as habit, so that like whenever you are doing this analysis, you should write all these things down, whether they are relevant or not, right? See, some cases m may be 0, but that shouldn't prevent you from writing the value of m, right? So, what are the values of n and m here? N is 1, m is 0, right? So, we have a pole at minus 1 over capital T, right? Ts plus 1 equals 0, right? So, you need to solve Ts plus 1 equals 0, s equals 1 minus 1 by capital T. As far as zeros are concerned, there are none. Okay. So, this implies that for stability, what should happen? T must be positive. Okay. So obviously, when you talk about, we will assign a physical correlation to this capital T. So, you will see that stability requires that it should be positive. Okay. So, we are going to have a pole at minus 1 over capital T. Okay. That is what we are going to have for this particular course, for the particular system, right. So, now what I am going to leave you with are these questions. Okay. So, you calculate the unit step response, okay, unit ramp response, and the unit impulse response of the system. Okay, that is a homework which I am going to leave you with. We would restart from the same point in the next class, right. So, calculate the unit step response means what do you use for u of s? U of s should be 1 by s, right. Unit ramp means u of s should be 1 by s squared, right. Unit impulse means u of s is 1. Okay, so please use this u of s. Pretty straightforward. Okay, it shouldn't take you more than 5 minutes to calculate all the 3 responses. Please get expressions, make observations. Okay, what do you observe? Okay, from that, and then you come back to the next class. We will restart our discussions from here. Fine. Okay, thank you.